Okay, so good day. So this is a recorded lecture on uh, undamped force vibration. Okay, so remember, we've already derived, no, this one, you know, this is an damped free vibration. Okay, oops, here's the PDF. Damped free vibration, and then okay, so for undamped free vibration, so the equation of motion will be mu double dot plus ku is equal to force as a function of time. And in this case, it's harmonic force. It will be P naught sine omega bar t, or P sub 0, no? Sine omega bar t. Take note, I'm mentioning omega bar. No? So omega bar is the frequency of the force. Okay. So for example, this is your SDOF structure. Again, this SDOF has its natural frequency, which is dependent on its mass and stiffness. Okay. But when there's a force being applied, a harmonic force, for example, in the form of P sub 0 sine omega bar t. For example, M and K, so we call that omega, or the natural frequency. Okay, so we're trying to find the response of this single degree of freedom structure from this harmonic force. Okay, now this is now a non-homogeneous differential equation. And according to differential equation, as the solution of non-homogeneous is the total solution is the combination of the homogeneous solution, no, and the particular solution, or the non-homogeneous solution. Okay? We've already derived, no, the solution for the homogeneous part. So, mu double dot plus ku equals 0. Alam na natin to. This is the undamped free vibration. Okay? So the solution for this is what we call the particular solution. That's why yung assumed solution natin will have a subscript of P. So meaning U sub P, particular solution. Okay? So instead of using C1 and C2, from here, no, we're going to use G1, G2. Then sine omega bar T plus G2 cosine omega bar. So this is our assumed solution. Okay? Just like what we did last time, we find the first derivative. No? First derivative of this one, diba? Derivative ng sine is cosine. Cosine omega bar t. Derivative of omega bar t is omega bar. And G1 here. Then derivative of cosine is sine. So sine omega bar t. And it's now negative, no? Because it's a sine. It's a sin. Then derivative of omega bar is omega bar t is omega bar. Okay, G sub 2. That's the first derivative. Okay, then finding the second derivative, u double dot, okay, is equal to negative G1 omega bar square sine omega bar 2 omega bar t minus G2 omega bar square cosine omega bar t. Okay. Then substitute natin yan sa assumed solution here. So you have now u double dot, plug in here, and you have this U, plug in there, okay? So expand, okay? Then you will have this. Ito nga yan. This is U double dot, while this is your U, okay? Then algebra, no? Get the common factor. It turns out we have G1 sine omega bar t and G2 cosine omega bar t with a common factor of k minus omega bar square m, k minus omega bar square equals p sub 0 sine omega bar t. Okay? Now, if you have this kind of equation, no, wherein yung nasa right side sine omega bar, and tapos meron ka ring sine omega bar sa left side. So, this will not happen na magsasabay yung sine and cosine. So, therefore, dahil occurring si sine omega bar dito, then meron ka ding sine omega bar dito, this term here is equal to 0. Okay? So, if we will rewrite that, so you have k minus omega bar square m, and then G2 cosine omega bar t is equal to 0. Therefore, G2 is equal to 0. Okay? So that's your first arbitrary constant. Then, may eliminate to. So, matitira itong this one and this one. And since common yung sine omega bar t, makakancel out yun. So, matitira is this one. K minus omega bar square m g sub 1 equals e sub 0. And transpose this, you will now find g sub 1. G sub 1 is equal to p sub 0 over k minus omega bar square m. Omega bar to, hindi ko lang kalimutan. Okay? So, meron na tayong G1, meron na tayong G2. Then, you can now plug into the assumed solution, U sub p. Okay? Since this term is 0, ito na lang matitira. Okay? So, you have U sub p is equal to G1 sine omega bar t. Okay? Now, further down, you can see that G1 is equal to this. Ano nangyari yun? Algebra lang, no? Because remember, M and K is what? That's omega. No? That's square root of K over M. So, omega square is K over M. So, algebra lang to. You can transform this into this. Okay? Wherein omega bar over omega is what we call, hindi ko lang nasulat dito, no? So we now introduce a formula beta, which is omega bar over omega, which is what we call the frequency ratio. Frequency ratio. Okay? So it is a the ratio of the force frequency and the natural frequency of the system. Okay? So you can now uh, have an idea, no? Let's say, for example, omega bar is equal to omega. What is that? Therefore, beta is equal to 1. So, beta is equal to 1. And that is what we call a resonance. That's a phenomenon. No? resonance phenomena. Resonance. Okay? Even that, no, may dami ng application, no, as you will observe, no. For example, no, let's say magkaroon ng earthquake. You have so for example, this last time merong earthquake sa Abra. Let's say Abra is here. Then we are here in Manila. So let's say the epicenter is at Abra, of course, no. Then the ground motion there is sobrang dami, sobrang bilis. Okay? So what is the frequency there? What's the frequency of the earthquake there? Remember, omega is the, sabi na, omega bar, no? Omega bar is the number of cycles, di ba, per second. That's your frequency, number of cycles per second. So, in a given second, in a given 1 second span of earthquake, sobrang bilis, so there's a lot of cycle, therefore, omega bar is large. Yun lang yun natin para madaling magets. It's large, no? It's too high. Now, when that earthquake travels to the Manila, of course, naramdaman natin, but it's not that uh, uh, large, no? It's not that uh, high, no? It's not that destructive, no? So the seismic wave might be something like this, no? See, right? No? So the number of cycles per second is relatively, no, is small, no? So we can say omega bar here in Manila is small. Okay? Now, what is the relationship of omega and frequency and period? No? From the formula, T is equal to 2 pi over omega, right? No? That's the formula. Therefore, it means that generally it's inversely proportional. No? If omega bar is large, therefore the corresponding period of the earthquake is small, no? Or short, right? Wherein here, if omega bar is small, the corresponding period is uh, short, large, large, or big. Okay. Now, relating to resonance. Okay. So that means the 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 frequency or the period of the structure or the period of the earthquake will resonate to the short period structures. Okay? Magre-resonate siya most likely sa short period structures. Okay, now, ano ang period ng structures natin? For example, sa plates nyo, di ba? Ang rule of thumb natin na tinuro ko sa period is, diba, T is about roughly 0.1 times the number of floors. Okay? So, if you are 2-story, 0.1 times 2, that's 0.2. If you are 5-story, like your plate, 0.1 times 5 is 0.5. That's a pretty short period structure. Okay? Now, for large period structure or long period structure, maybe high rise, not to exaggerate, no? High rise. T, or let's say 10 story, sabihin natin 50 story. 0.1 times 50 is about 5 seconds. Okay? That's it. Therefore, it shows that, yun nga, since the period of the earthquake is short or is small, it will resonate to short period structures. Mas madadamage yung mga short period structures. Which happens. Di ba? Pag nakita niyo yung destruction sa Abra, ang dami nag-collapse na 2-story, 3-story. Okay. Well, ibang usapan yung construction methodology nila. No? So most likely, that's the main reason also. But of course, since yun nga, the period of the earthquake, seismic wave, or the megabar is large, that it will resonate to short period structure, that further uh, justifies the collapse, causes the collapse. Ibang usapan kasi yung proper construction. No? Although short period yung structures mo, if you it's properly ano naman, constructed, no, you follow the seismic detailing of the code, there could be damage, no, but not collapse. Okay, but anyway, damage. So the idea is, with this kind of resonance, no, with the with the idea that the the seismic wave will resonate the short period structure, therefore they will have damage. Okay? Okay? Whereas when pagdating sa Manila, it's already small, therefore it will resonate to relatively large period structure. Okay? So kaya makita niyo no, when there's a seismic wave, 'di ba, may times na nag-sway yung mga high-rise building, no, yung mga swimming pool, 'di ba, sa taas, nag-ano pa, no, natapon, no, yung water. Okay? So, yung mga high-rise building, there's a possibility of resonance, but it doesn't mean na may damage, no? Okay? So, kaya mas kawawa yung mga short period structure near the epicenter because that will resonate to them. Okay? So, that's one of the application of this concept. Okay? And also, so by substituting G1, so this is now your U sub P. Okay? And what do you notice here? You notice that there's a term P sub 0 over K. And what is that? From matrix analysis, no, last sem, di ba? We've been using P equals SD. Or if we can transform that into something like P equals KQ. Yeah? Its force is equal to stiffness times the displacement. Okay? Therefore, U is equal to P over K. Therefore, this term here is the static deflection, no? Static deformation. No? And this term is basically a multiplier. No? So the dynamic deflection, U sub P, is basically the static deflection multiplied by a multiplier, no? Which is this. And the multiplier is a function of your beta, the frequency ratio. So you can imagine now that if there's your beta is equal to 1, the multiplier will become large because it will amplify your static deflection. Okay, that's the application of this formula, or the physical meaning of this formula. Okay, so that's it. So that's your U sub P, and as I said earlier, the total solution is the combination of this homogeneous and the particular solution, which is this. Okay, so if we will continue. Okay. So U of t is C1 sine omega t plus C2 cosine omega t plus this U sub p at rest, no? If you substitute at rest, yan, C1 sine times 0 plus C2 cosine times 1 because remember, this is 0, cosine 0 is 1, so C2 times 1. Okay? Bakit naging 0 si U sub p? Well, nag-0 siya because if you substitute 0 here, magiging sine 0, which makes this term 0. Okay? And for C2 is equal to 0. Okay. C2 is equal to 0. Yeah, because U sub 0 equals 0. Okay, because what causes the deformation is they call this the force, no, the force, harmonic force, right? That's why U sub 0 is 0. Okay, so C2 is equal to 0. And then to obtain C1, find the first derivative. This is first derivative, I think. Okay, okay. So here, yeah, tama. Ito na, sinubstitute na yung C2, no? Then find the first derivative of this, so becomes C1, ito, derivative of this is cosine, right? Then derivative of omega t is omega, and this is constant. Then derivative of this is omega bar cosine omega bar. Okay? Then substitute again, substitute t equals 0 at rest condition. Then here, okay. So, oops. So, ayan, so substituting again sa u sub 0 or u dot or initial velocity is 0 kasi nga the harmonic force will cause the deformation in the motion. So initial the velocity is 0 here. Yeah. So C1 omega because cosine 0 is 1 here, no? At t equals 0. So that's C1 omega. This one is also 1. So you have P sub 0 over K 1 minus beta square omega bar equals 0 equals the initial velocity. Therefore, C1 is this. Okay. So you now have C1, you now have C2, plug in to this. Yeah. Here, you have this. Okay. Again, if beta equals 1, ito yung magiging this. Where in resonance, this becomes your solution to the equation. Okay, this will be an assignment, no? Because remember, if beta is equal to 1, tingnan nyo, 1 minus beta squared. That becomes 1 minus 1, di ba? So 1 minus 1 is 0, which is not allowed. No? Hindi pwede kasi nga magiging undefined yung ano mo, sagot mo. So you will need to use Hospital's rule or hospital's rule, yeah, from calculus, yeah, to obtain this solution. Okay, mag-derivative pa kayo. Okay, and so I'll leave that as an assignment. And yun nga, if beta is equal to 1, the response will be something like this. So mag-amplify. Okay, so I think that's all for undamped force vibration. Now, hindi ko na ipapakita yung derivation for the damped force vibration. Masyado siyang mahaba. No? Okay. But the equation is this. Haba, no? Okay. So, which is similar to what we have earlier. Yung may P sub 0 over K, no? Which is the particular solution. And this one, yung may C1 sine saka C2 cosine, that's the homogeneous solution. Now, if you will notice, ito yung plot niya. Yan, ito yung plot. So the total response is the blue. Total response. And at, at a certain time, mawawala siya. Ano yung matitira? Yung steady state response. Right? So what does it mean? So, for engineering purpose, for design purpose, ito yung mas importante sa the steady state response or the particular solution. Huh? So, yun yung physical meaning, no, of this differential equation. The particular solution is the steady state response, which is the important thing sa ating engineers. Ito yung gagamitin natin sa design. Okay? Because itong homogeneous solution part is just a transient response. Diba? From the word transient, nawawala din yan. Hindi siya steady. It will just occur for a while. But then at a certain time, mawawala siya. Unlike ito, this is a steady state. Well, because as you can see, nandun yung force mo eh. Nandun yung force component. Okay? Nandito yung static deflection mo. Okay? So, hindi siya mawawala. Okay? So, that's the physical meaning of the particular solution in the homogeneous solution. So, we can now solve the problem. I think the problem is saan ko siya pwedeng ilagay? So, I believe well, sinold naman na pala last time. So, mag-assume na lang ako ng single degree of freedom structure. Having mass and stiffness. Okay. Na-demonstrate ko na rin kasi yung ano, free vibration, no? So, lagyan natin to ng force. Then, dito yung spreadsheet natin. Yeah. So, for example, I have a mass of, what's this? 25 kilonewton, no? So, ang magiging, anyway, na-solve naman na to last week, no? May idea na kayo dito. The mass will be like this, 2,548.42 kilogram. Bibigay ko naman dito ng spreadsheet, no? So, I can input here 25 kilonewton. Next is, what's the stiffness? I'll be using 3EI over L cube because it's a cantilever. I'll model a cantilever column. So, fixed dito sa baba. So, yun na, 3EI over L cube. And the section is, say, 0.2 by 0.3 cube, for example. I'll check with my SAP software here kung ano nilagay ko. No? So, anyway, ito, 0.2 by 0.3 cube, for example, that's the inertia. The length is 3 meters, the height. So, the corresponding stiffness is this. So, using ko to. Ngayon ko lang itong 3, for example. Yan. So, I can now get my frequency. Square root of K over M. And that's your frequency, 62.64. Which corresponds to 0.1 second. 0.1 second. So, kumbaga, in the context of structure, it's a one story or bungalow. Sabihin natin, one story. Pwede rin naman mga two story. Point. Okay? So, 0.1 second. Now, I'll be applying, for example, is 100 kilonewton to. And so, the applied force will be, for example, balik ko dito para makita niya. The applied force will be 100 kilonewton sine omega bar P. Right? Let's find out the response, no? Now, I'll choose an omega bar, for example. So, di ba, ang omega natin of system, 62.64. Let's say, I'll choose an omega bar of 60. Ano natin, 60. Then, implementing the equation, ito yun. I think ito yun, this one. So, undamped force vibration. Yan, kita nyo? So, meaning ito yun. Formula here. So that's the formula. So P sub 0 over K. Yeah, this is the P over K, which is this one, times 1 minus beta square. Okay. 1 minus beta square. That is E10. Beta. G2. Okay. That is basically K minus omega bar square M na pala, no? Okay. Itong other ito, format. Omega bar K minus, that's E6, yeah, minus omega bar, okay, omega bar square, and then M, okay, so same, no? So basically, so this is the response of the system, and its plot is this, okay? Ibigay ko naman itong spreadsheet. So as you can see, nandun, no? Because we assume an omega bar almost near or almost 1, because 60 divided by 69, that's almost 1. Ito yung naging response niya. Okay? Now, if I assume a different omega bar, litan ko, no? Kung 30 na lang. Kita nyo? Nawala yung resonance effect. Okay? That's it. Ganun lang, no? Ganun lang. I-implement lang natin to. Okay? So, para mas ma-appreciate no, ito, nag-SAP2000 ako because, ano nga, ito kasi may animation, no? May animation. So, I'll show you here, ito yung, let's check kung ano yung define kong section niya. Range section, define. Yeah, 0.2 by 0.3. Same. And then, it's a steel material. F550 is steel material. Then, 3 meters pa to. I-unlock ko muna. Para makita niyo yung property, right-click lang ako. Yan, it's 3 meters. Length, 3 meters. Okay, so same. Same yung inertia, same yung length, same yung elasticity kasi steel to. How about the mass? 25 kilonewton. Display natin yung object load assignment sa joint. Okay, sa dead load. Ayan, so yun nga. It's a 25 kilonewton. Meaning, this will produce a 0.1 second period. Yeah, period. So the omega bar is 62.64. Okay? Okay, then, so magde-define ako ng harmonic force. So para mag-define ng harmonic force, functions, time history, ito siya, yung sine wave. harmonic sine wave, sine force. Modify show, pakita ko lang. 0.105, yun nga. 0.105, diba? Remember, our period is 0.1 based sa calculation. So, yan yung nilagay kong omega bar niya, or the corresponding period. And then, amplitude, 100 kilonewton. Okay? 100 kilonewton. Okay, so ito yung mga graph. Okay. Kasi ginawa ko siyang how many seconds? 10 seconds, no? Dinamihan ko no? Okay. So, force sine, yan yung harmonic force. Para ma-define ko siya sa ito siya. Uh, basically, it's a time history analysis. Modify, show. Ayan. So, it's a linear. We're assuming elastic pa rin yung property ng material natin, nung section natin, all throughout the loading. And then, mga ano lang yan, output, ano lang yan, size. Then, sa dumping, 0, modify, show, additional dumping, ayan, 0. So, walang dumping kasi nga, yun yung nasa Excel natin. Okay, what else? Ayan. So, that's it. Ngayon, just additional information sa SAP2000, naglagay ako ng additional force display. Basically, if you will do that, just click the nodes, assign, joint loads, force. Okay. I'll show you. Ayan, mag-a-apply ako ng global X na force. 1 kilonewton lang. Kasi ganito yung style ni SAP no? Parang dahil 'di ba, nag-define ako ng time history load which is harmonic sine, no? Kailangan magde-define ako ng lateral force na parang yun yung susundin yung pattern. Okay? So 1 kilonewton. Hindi ko gagawin dito kasi gusto ko lang pakita, no? Supposedly, ita-type ko 1 kilonewton. But I'd like to show you na nagagawa ko na siya. Display, show, joint, force, apply. Ayun. Ginawa ko na siya. Kasi, yun yung parang isasabihin mo kay SAP2000 na ito yung pattern ng harmonic force. Okay? 1 kilonewton lang kasi, if you remember, naglagay ako sa time history ng load na niya mismo, amplitude. No? Nilagay ko na mismo yung amplitude. Okay? Yun ang ibig sabihin nun. And then, pag naman pinuntahan ko yung load cases ng force na yon, nakikita nyo, nandun yung pattern. Ayan. So, load pattern. So, kinocall ko ngayon yung pattern na to. Yung lateral force niya. Okay? So, that's it. Then, scale factor is just 1. Kasi nga, nakala na siya. Naka 100 kilonewton. Yun lang, no? And then, just run this. Okay, and then I'd like just to show the yung deform, show deform shape. Pakita ko lang yung modal period. Modal, apply. So, kita nyo, ang nakuha niya is 0.1 din, which matches our spreadsheet. Then, itong next body, if you will observe, iba yung load na nilagay ko dyan. Ito yung nilagay ko dyan. Pakita ko lang, display, object load, joint. Okay. Yan, 10 kilonewton. 10 kilonewton nilagay ko dyan. So, dahil, ibig sabihin, iba yung mass niya. No? Ito, 25 kilonewton, it resulted into 0.1 second. How about itong second body? It resulted into a 0.06 second. So, mas stiffer siya. Okay? So, this one is stiffer. So, this is flexible, 0.1 second. Relatively flexible. Okay? So the left is flexible, having a period of 0.1. Okay, this one. Ito naman, 0.06. Okay? And then, to display the deformation, uh, display, show plot functions, it's a joint 2 and joint 10. Tapos, with respect to time, then display lang. Kita nyo? So, yung joint 2, yung yellow. No? So, ibig sabihin, nag-resonate nga siya. Or hindi resonate. Hindi, may tawag dito eh. May technical term sa ganyan. Uh, motion. No? So, yung green, yung response nitong 0.06 na structure. No? Ito yung yellow response ng 0.1 second. Because nga, yung in-apply natin na force resonates dito sa 0.1 second structure, which is similar to this. Ay, sorry. Gawin ko nga itong no? Dito itong 60. Which matches this. So, if I continue further itong Excel natin, we will achieve the same pattern. Okay? Okay, so yung isa is 10 kilonewton, di ba? So, let's check 10 kilonewton. So, babaguhin ko to. Gagawin ko lang itong 10. See? Nakita nyo yung period niya, nagbago din. 0.06. And yung response niya, ito na lang. Yan yung maliliit. Okay? Okay. So, with that, so, I've just shown yung ano. Kasi dito sa software like SAP, may animation, no? So, yung response niya is here. Resonance, I think ito yun. Ay, hindi. Ito. SDF resonance. Yan. See? So, nakita nyo, no? Sobrang, ano, no? Sobrang nag-amplify siya. Yung isa, tahimik lang, eh, no? Yun yun. Okay? So, yun lang. Para lang ma-appreciate yun. Mas mahina nyo yung animation. So, you can imagine, no? Again, this is a 0.1 second structure. Ito, just 0.06. They have the same load. Yun nga, this is 100 sine 60, not T. Yeah. But they have a different response. Kasi nga nag-resonate, almost resonate dun sa 0.1 second structure. Okay? Okay, so that's it for this lecture about undamped force vibration. Okay? So next week is about parang ano lang natin, we will level up natin, no? We will proceed with response spectra. So we will basically do the same process, no? Magsa-subject ulit tayo ng, this time sa response spectra, ground motion naman. Ito kasi harmonic force. Okay. Set and by the way, no? Sa ba application pala dito, no? So bukod sa earthquake, no? In an actual experiment, no? You can do our harmonic force loading. No? Just to get the, for example, merong kang specimen ng beam column joint. Yan. Gusto mo makita yung cyclic response niya, no? Yung performance, no? Yung nitong joint na to. Okay. So, lalagyan niya ng harmonic force, cyclic, no? Then parang hanggang sa mawasak up to failure to get the response of the beam column joint. Okay? Because, for example, lalagyan mo yan ng iba't ibang klase ng bakal, no? FY, no? Let's say you're going to study yung walang reinforcement sa joint, no? Because the cyclic response will basically um, simulate the effect of earthquake. Diba? Because in an earthquake, yung structure mo, no, it's undergoing cyclic deformation. So, pupunta dyan, nagde-deform doon. Then, remember, di ba, yung moment diagram mo dyan is the maximum at the joint. No? So, by applying load here, you're basically applying a moment here at the joint, which is maximum. So, nasa-simulate mo yung response ng joint in an actual earthquake. And by getting the response of this joint, for example, a force deformation curve, malalaman mo yung capacity niya. And that capacity will be needed sa nonlinear analysis. Okay? So that's it for the undamped force vibration.